Here I have two rocks. One of them is quite a bit bigger than the other one. So I have a question for you. If I drop them at the same time, what will happen? Well, pretty much everyone is going to say they're going to land at the same time. But what about this? What if I drop one of them and then drop the other one a split second later? Obviously, they're going to start off with a little bit of separation. So whichever one I dropped first will hit the ground first. But the spacing between them, will the spacing as they fall increase as they get farther apart? Will it decrease as this one catches up? Or will they stay exactly the same and fall at the same rate?
Well, aloha everyone. Today we're going to talk about gravity and vertical motion.
When objects are in free fall on Earth, they accelerate at a rate of about 9.8 meters per second per second.
So it turns out working with gravity and vertical motion is actually quite easy because it still uses the same four kinematic equations that we used when we were just doing acceleration along a linear path in the x direction. Well, now the only difference is we're in the vertical direction, so things are moving up and down, which means there's a force of gravity we have to account for. And it turns out on Earth, like you heard me say, the acceleration is equal to, acceleration due to gravity, is equal to 9.8 meters per second per second. Sometimes you'll see people being a little bit more careful, and in most places on Earth, this actually rounds to 9.81 meters per second per second. And then some people will be less careful, and they might just even say that it's close enough to 10 that it really doesn't matter. So a lot of times you'll see any of these numbers, and you can get very precise numbers online for in your part of El Paso or in your part of the world, what is gravity at your elevation, at your part of latitude, because those sorts of things change gravity just slightly, the minerals in the ground, those sorts of things. But for the most part, we're going to assume that gravity on Earth is equal to 9.81 meters per second per second. Now, to indicate that this acceleration is specifically for gravity, and it just doesn't happen to be that there's a car that's accelerating at that rate, we're going to tend to use the letter G to represent gravity. But remember, G is an acceleration. G is 9.81 meters per second per second. So all the rest of the kinematic equations still work, and we can keep on using them to solve problems. For instance, let's take a classic example. Let's say that there's somebody standing on, I don't know, on top of a cliff here or something, and they're holding a ball, and the distance here happens to be, I don't know, let's make it 4 meters. So the distance from the ground to where the ball is 4 meters. And I want to know how long will it take the ball to fall to the ground. Now, before we start doing this problem, there's a couple little caveats we need to talk about. All objects on Earth are going to accelerate at 9.81 meters per second due to gravity. However, some objects have other forces acting on them that cancels some of that acceleration. Things like a piece of paper, or a feather, or a person wearing a parachute. Things that have a lot of air resistance are going to fall slower, not because gravity is any weaker on them, but because air resistance slows them down, keeps them from continuously accelerating. Obviously, if you had something like a jetpack or one of those water packs that shoots water out the bottom, that would also probably slow your fall. However, in this course, for the most part, unless we say otherwise, we're going to assume that air resistance is so small it's not going to make a difference here. So we're going to assume air resistance is negligible. Okay, so this person is going to drop the ball, and he's going to drop it from a height of 4 meters. So we're going to start by making a table. And that table, since we have our diagram drawn, we know a couple things. Distance is going to be, or displacement, I guess it is, it's going to be 4 meters. Oh, and it makes sense here, since the ball is going to fall down, it's going to have a final velocity downward. The acceleration is downward. I'm just going to call downward positive for the sake of this problem. You could use a negative if you want to, but that would make things harder with more negatives running around. We don't need to do that. V initial. Well, he's dropping this ball, so V initial has got to be 0 meters per second. If he were throwing it up, if he were throwing it down, it would be something different. V final, the final velocity, these are vectors by the way, V final, we don't know. The acceleration we do know, and it's 9.81 meters per second downward. And do we know the time? No, not yet. Okay, so now that we have this, we see we have a D, we have a V initial, we have an A, and we're looking for time. That sounds to me like kinematic equation number 3. This equation, D equals VI times T plus 1/2 AT squared. Vector there, and vector here. Now in the previous video, you might have heard me say that solving this thing for t is awful because it's going to require the quadratic equation. Well, most of the time. But sometimes there are little tricks you can use to help us solve this problem. In this case, before we do anything, I'm going to point something out. V initial happens to be 0. So that means V initial times time will also happen to be 0. So this piece, everything before the plus sign, doesn't matter. So our equation is going to be a little bit simpler to solve because it's only going to be this. D equals 1/2 AT squared. Now I can solve this for t without having to use the quadratic equation. I'm going to multiply by 2. So 2d equals AT squared. Now I'm going to divide by a. So 2d over a is equal to t squared. And then finally, to get t by itself, I'm going to take a square root of both sides. We're going to get 2d over a, the square root of the whole thing, is equal to t. Now that we have t by itself, we can go ahead and plug in numbers here. So this is equal to the square root of 2 times a distance of 4 meters divided by our acceleration is 9.81 meters per second. This is equal to, grab a calculator, and we get, looks like it's 0.903 seconds. Let's see if that's anywhere close.
I'm going to drop this rock from a height of about 4 meters. Yes, I measured it. All right, let's go. In 3, 2, 1, go.
So how fast was that rock moving when it hit the ground? Because the timing looks like it was pretty close to accurate. So our second part of this question, letter B, is going to be how fast is the rock going as it hits the ground? Now, I'm not asking about after it hits the ground. I mean, obviously it comes to a stop and that goes to zero. When you hear a question like this in physics, they're asking at, it's accelerating, it's accelerating, it's accelerating. What's the fastest speed it's going right before it runs into the ground and slows down and stops? Well, in order to calculate that, we can use two of the kinematic equations. Kinematic equation 4 would work here, but kinematic equation 2 is going to be a little bit easier. So, V final is equal to V initial plus A times T. Vector signs. And I'm going to solve for V final. Oh, it's already there. So all we need to do is plug in some numbers. V initial is 0 meters per second plus 9.81 meters per second times 0.903 seconds. And when I do this, I get 8.85, let's round that to a 9, meters per second, because that squared and that seconds go away. Okay, so 8.859 meters per second is going to be how fast that rock was traveling when it hit the ground. One thing that we might want to be careful about, however, is that not all vertical motion is from something that is dropped. Sometimes people throw objects upward. Sometimes they throw objects downward. And when they do this, it is still vertical motion, assuming they throw it straight up or straight down. So because of that, we want to see what happens if we have an object that we throw straight up. Let's try this. Let's imagine we have a person here, and he has a ball. And he's going to take this ball and he's going to throw it upward with an initial velocity of, let's make it 7 meters per second. Pretend that's vertical. And I want to know a couple things. Letter A, I want to know how long does it take the ball to get to the top of its path. And then letter B, I'm going to want to know how high does the ball go? Okay, so how long is it going to take this ball to get to the top of its path? So it's going to go right? So when it gets here, how long did it take to get up there to the top? And how high did it go? Okay, so we start by thinking about what are the pieces that we know. And we're going to make ourselves a table. The table is going to start with displacement. We don't know that. V initial, we're given in the problem, that's 7 meters per second. V final, we'll talk about in a second here. A, we know has got to be gravity, and it's a 9.81 meters per second. And finally, time, we do not know time, that's what we're solving for. So just looking at this, we see we know two of the variables, but we can't find anything unless we know about a third, so we have to think a little bit more about this problem. As this ball rises, let me grab this ball here. As this ball rises, it's going to start off fast and slow down and slow down and slow down and slow down. And eventually it reaches the top of its path. And then it's going to reverse direction and start falling faster and faster and faster. But just for an instant, right at the top of its path, its velocity is going to be 0. If you watch very carefully when somebody throws a ball up into the air, just for an instant, the instant that ball comes to a complete stop, assuming they threw it perfectly upward. If they didn't go through perfectly upward, it's no longer rising, but it's no longer not falling yet either, so it's just traveling a little bit sideways. When this happens, that means if we're looking at the time it takes to get to the top of its path, the velocity at the top, the final velocity in this case, is going to be 0 meters per second. We also need to be a little bit more careful about our directions too, because even though the initial velocity is upward, gravity is downward. So we need to choose a direction to call positive. Just thinking about it, I know the initial velocity is upward, the displacement is going to be upward, the final velocity is going to be 0, and the acceleration is going to be downward. Well, we have 2 ups, 1 down, 1 doesn't get a vote. So because of that, we're going to say upward is positive in this problem. If we make upward positive, this 7 is positive, but gravity, 9.81 meters per second, must be negative. Okay, we have 3 variables. Now we can solve for how long it takes to get to the top of the path. Again, we have v initial, we have v final, we have acceleration. So it turns out the correct equation to choose here is going to be kinematic equation number 2, which says v final equals v initial plus a times t. We need to solve for t. So here's what it looks like. V final minus v initial equals a times t. So all I did was subtract v initial. Then I'm going to divide by a. V final minus v initial divided by a is equal to t. Now I can plug in some numbers. V final is 0 meters per second minus v initial was 7 meters per second divided by the acceleration is a negative 9.81 meters per second. This is equal to, and when I do this, I get 0.71, round it to 4. And what are my units? Well, I have meters per second minus meters per second on top, which means it's just meters per second on top. I have meters per second squared on bottom, so meters and meters. Seconds cancels one of those. I have seconds on the bottom of the bottom, which comes up to the top as seconds. So 0.714 seconds is going to be my unit for that. So it takes about almost 3/4 of a second to come to a stop up at the top. Okay, how high does that ball go? Well, there are 2 equations we can use for this. We could use kinematic equation number 3 or kinematic equation number 4. But it's going to be easier to use kinematic equation number 3 in this case because it's already solved for d. So d is equal to, by the way, I was very sloppy here. Those all have vector signs over them, vi's, a's, and vf's, right? So put in some vector signs. All right, there we go. So displacement is equal to v initial times time plus 1/2 a t squared. In this case, I am going to be, I'm solving for d, so it's already solved. So all I need to do is plug in some numbers. D is equal to, my v initial was 7 meters per second, times my time is 0.714 seconds, plus 1/2 times my acceleration is negative 9.81 meters per second, and my time is 0.714 seconds. If you're going to mess up this equation, by the way, you know what you're going to forget? The squared right there. D is equal to, I got 2.497 meters. If you got something relatively close to that and it's only off by like that digit, that's probably just rounding error. If you got something way different, that probably means you typed something wrong into your calculator. Remember, when you're typing these numbers into your calculator, you don't type the units in. So you're going to type 7 times 0.714 plus 1/2, or maybe you just put in 0.5, times negative 9.81. A lot of people get confused about this. Do we put that into the calculator? The answer is no. That's a unit. You only put in a squared if it's part of the formula. So like up here, not unit. So that means this squared, yes, you put that one in. So times 0.714 squared. Sometimes, if your calculator isn't smart enough, you might have to follow order of operations and work your way through this. But I get 2.497 meters, which means the ball went about 2.5 meters upward. So let's circle back around to the question that we started the video with. Somebody is on top of a ladder. They drop one rock, and then the other a split second later. Turns out their masses don't matter. It doesn't matter if it's a big rock or a small rock, as long as air resistance is not significant on either of them. So we have two rocks dropped from the same height. Here we go. So boom and boom. Okay, one of them is bigger than the other, so I'm going to make that the big rock. And I'll tell you what, let's make this the small rock. There we go. Okay, so he's going to take these two rocks, and instead of dropping them at the same time, he's going to drop one, then the other. Let's say he drops the small rock first, and then drops the big rock. This rock is going to start falling, and it's going to be, I don't know, maybe about here when this rock is dropped. So, after a short amount of time, maybe a tenth of a second, let's say, what's happening? Well, this rock has traveled a little bit more. Maybe it's down here by now. And this rock has traveled a little bit, so maybe it's here by now. The difference is that this one has had significantly more time to accelerate. So this rock is not only farther down than it, it's also traveling faster than this rock. And as time goes on, that means that it's going to travel a greater distance, which means at the end of the next tenth of a second, it might be here, whereas this rock is barely getting to here. And so this one's velocity is now this. I should really be using a different color for this. Let's change that to red. So this is the second tenth of a second. So now this one is still traveling faster. The small one is still traveling quite a bit faster. So because of that, it's going to be going whoosh. And the larger one is going to be traveling slower because it hasn't had enough time to speed up. It'll take a little bit more time to get going that fast. Because of this, you can see that the small rock, or the rock on the left in this case, is always traveling faster than the rock on the right. Which means that they're going to separate, because the bottom rock is going to always be traveling faster than the top rock. Don't believe me? Let's see some proof.
So let's try it and see if we're anywhere close. I'm going to hold these two rocks out here. I'm going to drop this small one first, and then I'm going to drop the big one slightly after. Ready? Here we go. Did you see it?
So that's really all there is to it about gravity and vertical motion. I'm sure you'll probably have questions. I'm sure issues will come up. But those are the basics. So, mahalo for watching, and see you next time.